All right, so today we're moving on to section 8.2, day 1. Again, we're going to break this into 2 days to try and keep the size and the number of concepts down. Today we're going to take a look at the double angle formulas. And again, these are actually double angle identities, in that they are true for any angle that we choose to look at. Let me just run through what the 3 identities say. The way they're used is going to be pretty straightforward, and then I'll show you 2 examples that I think may give you some trouble if I don't go through them with you. Excuse me. All right. So when we talk about a double angle identity, what we're talking about is we're talking about something that looks like sine of 2 times theta. So here's our double angle, this 2 theta. So we're doubling our angle. So if theta is 30 degrees, we're really talking about the sine of 60 degrees here. We're doubling the angle and then taking the sine of it. Now, the way that you expand this to get the identity is you go back to what we did the last 2 days with the addition and subtraction formulas, and 2 theta can be written as theta plus theta. Well, we now know that sine of s plus t, in this case theta plus theta, is equal to sine of the first times cosine of the second plus cosine of the first times sine of the second. Notice that the first and second are both theta, so we have nothing but angle theta in there. And notice, even though they're reversed, these are really like terms. And so it turns out that this just gives us 2 times sine of theta times cosine of theta. So it turns out that sine of 60 degrees, 2 times 30, would be equal to 2 times the sine of 30 times the cosine of 30. So let's just see that specifically. So sine of 60 degrees, which we know is rad 3 over 2, is equal to the sine of 2 times 30 degrees. Now this is our theta. And so what we now have is we now have 2 times sine of theta times cosine of theta. That's equal to 2 times the sine of 30, which is 1/2, times the cosine of 30, which is square root of 3 over 2. When I multiply across, that gives us 2 square root of 3 over 4, which simplifies down to square root of 3 over 2, which is what we know sine of 60 should be. So you can see it actually working in this example. So sine of 2 theta, our double angle, is equal to 2 times the sine of regular theta times the cosine of regular theta. By regular theta, I mean 1 theta. Okay, now let's talk about cosine of 2 theta. And there's actually going to be 3 versions of this identity. But cosine of theta is derived from cosine of theta plus theta. Sorry, cosine of 2 theta is derived from cosine of theta plus theta. And this, we know, is cosine of the first times cosine of the second, even though they're both the same, minus, because of the plus, sine of the first, sine of the second, which tells us that this is really cosine squared theta minus sine squared theta. That is cosine of 2 theta. So notice, that is not the same as cosine squared plus sine squared equals 1. This is cosine squared minus sine squared is the same thing as cosine of 2 theta. Now, there are 2 other identities that come off of this one. Cosine squared theta minus sine squared theta is cosine of 2 theta. But we know that cosine squared minus sine squared can be written as cosine squared theta minus, and sine squared is really 1 minus cosine squared theta. That's cosine squared theta minus 1 plus cosine squared theta, which means that this thing is really equal to 2 cosine squared theta minus 1. And so we don't just get this identity, we also get this identity for this. Now, we have another one still, and that is cosine 2 theta is cosine squared theta minus sine squared theta. But instead of getting rid of the sine squared, can't I get rid of the cosine squared as well? The answer is of course. So now this is going to become 1 minus sine squared theta minus sine squared theta, which becomes 1 minus 2 sine squared theta. So anywhere where you could use one of these things, you could actually use all three. It just depends on what you choose to use or what serves your purposes, especially if we're working with trig proofs, which we will see more of in this section and in this chapter. Okay, so there are the three identities for cosine of 2 theta. So you want to memorize those things. Now, in your book on page 492, you guys are going to see a large list of identities. It does not have all of them in the gray box, but it does have the majority of them. There are also a couple on page 490 in the blue box at the top. You will not need to worry about section 8 and 9, the two bottom sections of the gray box on 492, as we will not be doing the sum to product and product to sum formulas. Okay, we've done sine of 2 theta, we've done cosine of 2 theta. Let's now do tangent of 2 theta. Tangent of 2 theta is equal to tangent of theta plus theta. And again, I'm deriving this for you. You don't have to write this step down. You just have to use the identity. This is tangent of the first plus tangent of the second divided by 1 minus tangent of the first times tangent of the second. That's going to be 2 tangent theta over 1 minus tangent squared theta. And there's our tangent of 2 theta identity. So tangent of 60 degrees would equal 2 times tangent of 30 degrees over 1 minus tangent of 30 degrees, and then square the tangent value. So tangent of 30 degrees quantity squared. All right. So for evaluating with these, it's going to be very straightforward. What I want to do is I want to show you guys how we actually go about using these in problems. And so let's take a look at the following problem. If cosine of alpha is equal to 2 over 5, make that a little cleaner. And they tell us that alpha is between 3 pi over 2 and 2 pi, which means we're in quadrant 4. We want to find sine of 2 alpha, and cosine of 2 alpha. Well, the problem is we have no idea what's going on with alpha. But we do have some information about, with 2 alpha, but we do have some information about what's going on with 1 alpha. So what we're going to do is we're going to draw our picture. We know our triangle is going to be sitting in quadrant 4. We know that our angle is our alpha. Here's our 90 degrees. Cosine is adjacent over hypotenuse. So we know that 2 squared plus b squared equals 5 squared. So b squared is equal to 25 minus 4 is 21. B then is equal to plus or minus the square root of 21. And because we're in quadrant 4 and this represents our y-coordinate, this is going to be negative square root of 21. So hopefully that doesn't give anybody any issues. Now that we filled in our triangle, now we can evaluate these. So I take sine of 2 alpha, and I have no idea what the 2 alpha picture looks like. But I do know that sine of 2 alpha expands into 2 sine of alpha cosine of alpha. By expanding it, now I have single alpha angles, and I do know what the single alpha picture looks like. So this is going to be 2 times sine, which is opposite over hypotenuse, negative rad 21 over 5, times cosine, which is adjacent over hypotenuse, make this over 1. And so this then becomes 4 negative times the square root of 21 over 25. That's the sine of 2 alpha. Now we're going to do the same thing with cosine of 2 alpha. We're going to start by expanding it, and I'm going to choose to use the cosine squared alpha minus sine squared alpha. But you could use whichever of those 3 from the other page that you wanted. You could use any of these 3. I'm choosing to use the top one. That's going to be cosine of alpha squared minus sine of alpha, the whole thing squared. Cosine, we know, is adjacent over hypotenuse, 2/5. Sine we know is negative square root of 21 over 5. This becomes 4 over 25. Minus, when I square this negative, it becomes a positive, and I get 21 over 25. And so this ends up being negative 17 over 25. And so that is our cosine 2 alpha value. Okay, I just have one more quick example that I want to show you today. Again, we're going to be keeping this video on the short side, which I think is better whenever possible. Feel free to pause this or rewind if you need to, but I'm going to keep moving on since you have that control. We're now going to look at what happens if they tell us that x is equal to 2 times sine of theta. And they tell us that theta is between 0 and pi over 2, which means we're in quadrant 1. And we want to find sine of 2 theta. Well, again, we don't know anything about the double angle 2 theta, but we know something about theta. This looks very different than what you were just given. On the last problem, what were we given? Well, on the last problem, we were given that cosine of our single angle is equal to a value. We're not being given that on here, or are we? And the answer is we actually are. All you have to do is one extra step. Notice that if x is equal to 2 sine of theta, that means if I divide both sides by 2, I get sine of theta is equal to x over 2. There's my opposite over hypotenuse ratio for me to draw my triangle with. So you just do that first step. You go to the quadrant that you're in, which in this case is quadrant 1. You have your angle here, your right angle here. Opposite is x. Hypotenuse is 2. There are no negatives to fill in at this point because we're in quadrant 1. Now, a squared plus b squared equals c squared. So we know that a squared plus x squared equals 2 squared. So a squared is equal to 4 minus x squared, which makes a equal to plus or minus the square root of 4 minus x squared. Do not square root that. There is no square root of 4 minus x squared that we can simplify. It is not 2 minus x. 2 minus x times 2 minus x is not 4 minus x squared. It's not even close. So please do not make that mistake. Some of you have been making that mistake, even though I warn you about it over and over and over. If you don't believe me, FOIL it back out after you pull it out and make sure it gets you back to 4 minus x squared. Okay. So what we're going to do now is we're going to find sine of 2 theta. Oh, I'm sorry, excuse me. We're in quadrant 1, so we know this must be positive, not negative. I apologize. Got ahead of myself there. Square root of 4 minus x squared. So sine of 2 theta we know expands into 2. Sine of theta, cosine of theta, which we know is 2 times sine of theta, opposite over hypotenuse, times cosine of theta, square root of 4 minus x squared. That's adjacent over hypotenuse. This is 2x square root of 4 minus x squared over 4. And obviously those cancel and give you x times the square root of 4 minus x squared over 2. There's our sine of 2 theta value. And obviously you could expand and find cosine of 2 theta or tangent of 2 theta using the same triangle. So that's it for today's lesson. We kept it under 15 minutes. I gave you just kind of the bare bones idea, but the rest of it should be pretty straightforward. Again, I would like for you to at least take a look at some of the easy problems, maybe knock those out, and we can tackle the harder ones in class tomorrow.